Hello guys, in this session we are going to analyze the results of molecular dynamic simulation of protein ligands in complex system that we have performed in the previous session, right, by using GROMACS software. Okay, so in this session we are just going to analyze the results, that is RMSD, root mean square fluctuation, root mean square deviation, SASA, hydrogen bonds, and this analysis generally suggests us how the ligand molecule and protein and ligand complex are generally the compatible with each other and how much they are stable, right? So generally we are going to see via this analysis how the structural changes are there, right? So we are going to just do some calculations, and yeah, we can calculate, we can analyze the results of our molecular dynamic simulation of protein ligand complex. So yeah, so we have to run some commands, right? So like we are going to perform the RMSD calculation. Okay, so GMX, and we have to go for the flag GMX RMS minus S MD dot TPR minus F MD dot XTC and minus N index dot NDX minus O RMSD. This time we are going to calculate the RMSD for protein C alpha RMSD. Okay, C alpha XVG, yeah, and minus TUNS. Then this flag is generally for the numbers in nanosecond, time frame in nanosecond. Okay, and also I will tell you how the command, if we don't use this flag, so we can got the time frame in picosecond, right? So yeah, so just we feed the protein and just C alpha. Yeah, there's the calculation, and this time we can analyze it via XMGRACE software. Okay, XMGRACE is generally the a tool, software that we can plot the various analysis of RMSD, RMSF, SASA, hydrogen bonds, and any other and many analysis we can plot via this XMGRACE software. Okay, so yeah, you can see there is the RMSD in this axis, and this axis there is the time frame, that is this is the 1 nanosecond, right? This is just for the understanding how we can perform the MD simulation of protein ligand complex, right? And for research publication case, we have to go for 100 nanosecond, 200 nanosecond, and also we can perform for 500 nanosecond if there is some major deviation and major fluctuations are in the RMSD and RMSF plots, right? So reviewer may ask in the replicates, like triplicates or something like this, right? So we have to perform the simulation for 3 times and 4 times to get the reproducibility of the RMSD and RMSF, and any other analysis we are going to perform in to analyze the structural changes of protein ligand complex. Generally we are generally we are going to analyze the structural changes of protein ligand complex, right, via MD simulation, via this RMSD and RMSF analysis. We are just going to just see how the structural changes happens in the protein and ligand complex after and before the MD simulation and before the complex formation, right. And then after the complex formation we have run MD simulation and perform some analysis like RMSD and RMSD to RMSD and DCCM and other many other like we can also perform the free energy binding free energy calculation via MMPBSA, MMGBSA, right. So we can also go for that in next session, right. In this session we are just calculating and analyzing the RMSD, RMSF and these structural changes basically, right. So this is the RMSD with respect to time, right. So yeah, and now I'm going to show you this nanosecond in picoseconds, right. So we just have to go for, sorry, we have to rename it PS, yeah, 3, yeah, we can have it action grace. And now yeah, you can see there's the picosecond, there's the time frame in picosecond, right. In previous plot there's the nanosecond here and 1 nanosecond, so 1000 picosecond is equal to 1 nanosecond, right. So there is no changes in RMSD plot or and RMSD itself, right, but just the representation of time in picosecond and nanosecond, right. So next we have to calculate the RMSD for ligand. So yeah, we just change it to lig, right. So 1 and 13, why 13? Because 13 number is assigned for the ligand molecule, right. So just go for 13 and yeah, we have the analyzed results of ligand molecule RMSD. Yeah, you can see there is some minor and little deviation or little fluctuations we can say, and these fluctuations in last that leads to continue or increase the length of time, length of the MD simulation of protein ligand complex to analyze how the structure changes, how the stability it will gain in how much time, right. Like this system can get in 50 nanosecond, 100 nanosecond, so this and so on, right. So this basically the prediction, this is just the prediction how much time it will take to stable the whole complex, right. In the this is the case of ligand molecule, right. But the protein is really stable and very compatible with protein. There is no major deviation and no major fluctuations are there, right. We have already seen in the previous plot of the protein ligand C alpha, right. So we can we should go for at least 50 to 100 nanosecond to check the stability of our complex, of our protein ligand complex, right. So yeah, this is the RMSD 0. Higher RMSD is 0.3 and the average RMSD we can say 0.8, yeah, 0.8, yeah, 0.08 or 0.2, yeah, something like this. Okay, so yeah, okay, so we are going for the next analysis, that is RMSF. Okay, I can show you the also the data. Okay, how the RMSD is fluctuating in data file, how is the look like. Okay, so yeah, this is the XMGRACE file via generating and the command, right? In the x-axis there is the frames, okay, and the y-axis there is the time frame. This is just the nanometer. Okay, RMSD, this is the RMSD, and this is the in the x-axis there is the time frame. Okay, and this is the RMSD. So yeah, you can see, right? So there is the 1000 picosecond, right? And the RMSD is 0.3079566 nanometer. Okay, so this file is look like this. So now I am going to go for the calculation of RMSF, right? Root mean square fluctuation, GMX RMSF minus S md.tpr. TPR file is very important, and also the trajectory file, that is XTC file, minus F md.xtc. We can also use the TRR file in place of XTC file, but I have not generated this file because XTC and TRR file are the same, right? Both file are contain the same information. So yeah, minus O RMSF C alpha. The RMSF we are generally look for the C alpha of a protein, right? Dot xvg minus n index dot ndx. Okay, so yeah, there is some, oh, okay, this is the flag is wrong, the input flag. Yeah, sorry, the RMSF is calculated for protein, so all the items I can say. Okay, we also just again calculating the C alpha protein. Okay, yeah, we have both the RMSF for RMSF C alpha and RMSF protein, that is all item. So XMGRACE, we are going to analyze both the files, C alpha and protein. So yeah, you can see there's the change. You can see the black line, right, and the red line. Red line indicates the all atoms of protein molecule, and C alpha means there is the C alpha carbon atoms, right? Only alpha carbon atoms. So there is, you can see the difference and the fluctuations of C alpha and all atoms. Like all atom RMSF is 0.3 nanometer, and highest RMSF is 0.34 nanometer, and highest C alpha RMSF is 0.12 nanometer, right? So there is the difference. This is the difference to analyze the results. So yeah, and we are going for next analysis, that is hydrogen bond analysis. So we can go for next command, GMX hydrogen bond minus S md.tpr minus f md dot xtc minus o minus number of hydrogen bonds hb dot xvg, right? So yeah, I also give the index dot ndx file. Yeah, there is some number. Okay, so first one for protein selection, the list is square feet, and 13 is for ligand. Yeah, we have the analyze hydrogen bond, and we can analyze and visualize via XM rays. Yeah, you can see there is the hydrogen bonds, there is the total two hydrogen bonds, and one hydrogen bond is very rich in respect to time. For the duration of whole MD run in 1 nanosecond and 1000 picoseconds, or we can say 1000 picosecond, there is the one hydrogen bond is very static and continuous and constant, but the second hydrogen bond is very unstable, we can say, right? So sometime in the 400 picosecond, 500 picosecond, and 615 nanosecond picosecond, so this hydrogen bond can appear, right? But one hydrogen bond is very consistent with the time, right? Like a ligand molecule is forming two hydrogen bonds, and one hydrogen bond is very consistent and very stable, right? So yeah, this is the hydrogen bond analysis, number of hydrogen bonds, and this is the time. Okay, so next command we are going to calculate the radius of gyration. So GROMACS gyrate minus s md dot tpr minus f md dot xtc minus o gyrate dot xvg for the protein, right? Yeah, we have the plot, we have the file for the radius of gyration. Open with XM rays, and now we have the results. This is the radius of gyration, very static and very consistent and very constant, right? And there is no major fluctuations are there, you can see, right? Very stable region. So yeah, there is the radius of gyration in nanometer and with respect to time, right? So this for the protein molecule. We can calculate all the analysis with all the index groups, like we can calculate the radius of gyration, RMSD, RMSF, and SASA as well for protein, C alpha, backbone, right? It's like I can tell you, this is the system, whole system: protein, hydrogen, C alpha, backbone, right? Ligand molecule, and also we can calculate for the protein ligand complex as well, right? So yeah, this all are the analysis, and finally we are going to analyze one more analysis, that is solvent accessibility surface area, right? So GMX SASA minus f md dot tpr minus f md dot xtc minus n index dot ndx minus O SASA dot xvg minus surface protein link, right? Yeah. There is some, okay, minus s, we have to give the input flag. Okay, the SASA analysis is analyzing the results, and we got the results. Okay, SASA exam grace, and now you can see, right? We can change the name as well. SASA, yeah, you can see there is the minor deviation in solvent accessibility surface area with the time, right? For the starting frame of 200 picosecond, there's the solvent accessibility surface area is about to 60 nanometer square to 64 nanometer square, and after that it will utilizing the 50 nanometer square to 60 nanometer square with the time frame for the medium mid time frame and last time frame, right? So yeah, this is all about the SASA analysis, solvent accessibility surface area. Okay, so you can write any of the legends. Yeah, this is the legends we can you can change, right? Yeah, I can name it as MDM2 NUTD1, right? And we can change the color, right? So yeah, this is it. So this customization you can customize according to you, where you want to put your legends, and how to customize it based on your, okay. So yeah, this is all about the RMSD and SASA, RMSF, and hydrogen bonds, radius of gyration, right? So yeah, this is all about the analysis. Okay, so we can also analyze the trajectory, how the protein and ligand moving thermodynamically, right? So we can go for VMD, and just use GROMACS file and trajectory file. Yeah, you can see. The representation is we are going to use the new cartoon, and we have to, there's a no ligand yet, and we have to yeah, there's the ligand, and we can, yeah, you can see there's the protein and ligand. Just we are going to analyze how the tightly bound this protein with residues, this protein ligand molecule is bound with the protein molecule, right? So I'm just going to normalize and stabilize the structure. And yeah, you can see it should not unbind with the residues, amino acid residues. It should be tightly bound in whole MD run, right? Yeah, you can see with the time frame you can see the how protein and ligand complex are generally moving with time and thermodynamic motion, right? So I can increase the speed, right? So yeah, this is like that. Okay, so this is all about the analysis, guys. Okay, and next session we are going to perform the MMGBS and MMPBS analysis, and other structural changes we are going to analyze via different analysis, like dynamic cross correlation or principal component analysis, right? And we can I can also show you how we can plot the 2D and 3D plots of energy minima, okay, of the protein ligand complex. So thank you, bye bye.